All right, let's talk about the last uh, type of equilibria that we're going to consider here. This is the mainly going to be solubility is what we're going to talk about here, the equilibria of solubility reactions. Uh, if you remember, we talked about in chapter, I forget the chapter number, but we discussed how you can have essentially too much of a solid tried to dissolve in a liquid. You can have more solid than will dissolve, and at that point the solid doesn't actually stop dissolving. Instead, what happens is, as the solid dissolves, some of the solid that had already dissolved and gone into solution actually recrystallizes. And so you have a dynamic equilibrium between the solid continuing to dissolve, but it being redeposited as well. Some of the stuff that is in solution already, like these here, starts to go back to being a solid again. And so when we have these saturated solutions, where we have something that is soluble, in water usually, and for our purposes in this chapter it's always going to be water, something that is dissolved in water, but there's essentially just too much. There's too much to dissolve. It will continue to dissolve, so this forward reaction is still happening, but it will recrystallize as well. Some of it will go back. It'll be at a dynamic equilibrium. So we have an equilibrium that exists here in these solubility type reactions. And so in this particular reaction, we have barium sulfate that is dissolving and turning into barium 2+, and sulfate in solution, and those are going back to being barium sulfate solid as well. So when we're writing the solubility product, is what we're going to call it, is what we're going to call the equilibrium constant for this type of reaction. Actually, let's go ahead and do that back here. Take a step back here. When we're writing the equilibrium expression for this, if you remember, we called it Kc before. That is always products over reactants. When we're talking about solubility reactions like this, we're going to give it a special name. We're going to call it Ksp, which is just the solubility product is what SP stands for, but it is still just going to be products over reactants. So we're not changing the actual math here, we're just giving it a special name, very similar to what we did with the acid dissociation constant. And so for this particular reaction, Ksp is just going to be barium 2+ times sulfate, because we only have one product and it's a solid. And if you remember, solids do not show up in the equilibrium constant. So the only thing we have are our two products, and this is actually going to be the case for everything that we're going to see. The number of products will change a little bit, because we could have 2 things, or we could have 3 things that are products, just depending on the molecule. But we will never have any of our reactants showing up, because our reactants are solids, and they will always be solids. So let's go ahead and practice writing the Ksp for these molecules here. And actually, this particular question is just asking, I guess it is asking for the solubility product as well. So we're going to write the dissolution reaction, and then we're also going to write the Ksp. So AgI is our first one here. This is silver iodide. So its reaction that's taking place is silver plus and iodide going into solution. And so Ksp for this particular reaction is just silver plus and iodide. So why don't you pause the video for a second and do the same thing with calcium carbonate. Okay, so with calcium carbonate, we have calcium 2 plus going into solution, and carbonate going into solution. So our KSP is just going to be calcium and carbonate. Calcium 2 plus times carbonate 2 minus. That is our KSP. Again, it is just the products, and just plug them right in. The next one, or the next two here, actually the next three, are going to be a little bit different. Go ahead and pause the video and try to do those as well. And actually, I'm going to erase the ones that I have up here while you work on that, because I'm going to run out of space pretty quickly. Alright, hopefully you paused the video and now you're back with what you believe are the correct answers for these. So that first one there, we have magnesium hydroxide, and it is dissolving into magnesium 2 plus and 2 hydroxides. What that means is our KSP is going to look a little bit different here, because now we have not only the 1 magnesium 2 plus, but we're going to have OH minus squared. Because remember, we take the coefficients and we plug those in as the exponent in the equilibrium constant, which is going to make the next one here even more complicated. So here we have MgNH4 PO4. And the reason I say it's going to be a little bit more complicated is because now we actually have 3 different things. Not just 3 different things, but 2 of them are the same, like OH minus. We actually are going to have here Mg2 plus, which is an aqueous phase. We're going to have ammonium, which is in the aqueous phase. And we will have phosphate, which is an aqueous phase. So it looks a little bit different now, but we are still just taking our products and plugging them in. In reality, we're still just doing the exact same thing we would do to any other equilibrium. It's just our only reactant is a solid. Alright, so then the last one here, we have a lot going on. Let's see, we have Ca5PO4 3OH, which is a solid. That is going to break apart into 5 calciums, 3 phosphates, and a single OH minus. I'm going to go and put the KSP down here since we kind of run out of room there. So KSP is again just going to be everything that could show up in the equilibrium expression, which in this case is just going to be, again, the products, because our only reactant is a solid. And so we will have calcium 2 plus to the 5th, phosphate to the 3rd, and a single lonely OH minus. That is our KSP value. Alright. I think I will pick up here in the next video. I think that's enough for one. I'm going to try my best to keep these videos relatively short. So we will pick up here with talking more about the solubility product in the next video.